For this lesson, we're going to take a look at the absolute value transformations. So we know when we did it for our original absolute value, y is equal to the absolute value of x, then we said that it's going to look like y is equal to x. When it's greater than or equal to 0, it's going to look like the negative version or reflected version when it is less than 0. We can do the same transformation process for any of these. So if I had a function y is equal to x minus 1, well, the absolute value of this would just be y is equal to the absolute value of x minus 1. If I take my original form, where it's just y is equal to x minus 1, then I'm going to get -5, -4, -3, -2, -1, 0, 1, 2, 3. And in this case, it's just going to look something like this. When I take the absolute value of that, well, the absolute value of 5 is 5. Sorry, -5 is 5, -4 is 4, -3 is 3, -2 is 2, -1 is 1, 0, 1, 2, and 3. And I'm going to get something that looks like this. Now, anytime that my function, in this case, y is equal to x minus 1, was greater than 0, the absolute value function looked the same. We can see that right here. They're overlapping, they're collinear, they're perfect. Any time that it was less than 0, it looked like a reflection in the x-axis, where if I followed along the x-axis here, then I can see that they are perfect reflections of each other. Take every single negative value and make it positive for y. I can do the same process with a quadratic one. If I take the absolute value of this quadratic function, it's just going to be y is equal to the absolute value of x squared minus 4. What are the only things that change? Well, the positive values would still be the same. The absolute value of those positive values are the exact same values. The negative values, like here, when y was -3, or here when y was -4, become +3 and +4. And once again, they become a perfect reflection in the x-axis. Do the observations from the first case match? Yes. Any negative value becomes a reflection across the x-axis. So if that's true, then any function that I draw out for you, you could always do the same process. All you need to say is that wherever the original function was positive, the new function is still going to be positive. Wherever it was negative, it's going to become a reflection. Like with example B, if my entire original function was negative, then my entire absolute value function is going to be a reflection across the x-axis and is going to be the positive version. Now, how does that affect the domains and the ranges? Well, in every single case, x kept going to the left and x kept going to the right, no matter what it was. It had no effect. Domain stayed the same. Now, what did it do to the range? If there was an x-intercept for f of x, then absolute value of f of x had to be greater than or equal to 0. If f of x was negative, with no x-intercept, then absolute value of f of x had to be greater than or equal to the max value of f of x. What does that look like? We can see here where it crossed below, then we know that suddenly that minimum point where it was negative here, my absolute value of f of x had to be greater than or equal to 0. It can't cross below that point. Where I had my max point here, where in this case, f of x had to be less than or equal to -1, my absolute value was f of x had to be greater than or equal to the positive version of that, +1. How does it affect the x-intercepts? No effect. X-intercepts stay the same. How does it affect the y-intercept? If positive, no change. If negative, becomes positive. So if I had a y-intercept at +1, then the y-intercept is still at +1. If my y-intercept was -3, it becomes +3. And that's pretty much it. All right, go ahead, get some practice.